Hey, everybody, and welcome to the latest episode of the Let's Clear the Air Energy podcast. Stuart and I are joined today by Dr. Ramesh Agarwal. He is extremely experienced, and he's the William Palm Professor of Engineering at Washington University in St. Louis. He has 4 or more decades of research and study. He's made significant contributions to aerospace, energy engineering with research covering computational fluid dynamics, or what you might hear referred to as CFD, wind and solar energy, energy efficient buildings, chemical looping, combustion, and geological carbon sequestration. Dr. Agrawal has authored or co-authored more than 600 scientific publications, and it is a fellow in 23 professional societies. He has an array of major honors, including the Reed Aeronautics Award from the American Institute of Aeronautics and Astronautics. And what caught our eye, as I read that's an abundant amount of things. What caught our eye was a recent article that he wrote on carbon capture. So Dr. Agrawal earned his PhD in aeronautics sciences from Stanford, and we're thrilled to have you join the podcast. So thank you so much.
Well, thank you very much for the introduction. And I'm pleased to be a part of this podcast. And I am here to entertain any questions that you may have based on the article or beyond the article that I had written for what is called the conversation. My last information is that it has already been read by over 70,000 people. So it has got a good um, review by a lot of people. Good, and I am really pleased to be here.
Excellent. Well, sometimes we throw around it's not rocket science, but it's pretty rare that we have a rocket scientist on here. So thank you for joining. We covered quite a bit in your background, but please, if you could dive into what caused you to start focusing on energy systems and carbon capture specifically in your research.
So, as you mentioned before, that I have a PhD from Stanford University, and that goes back in 1975 in aeronautics. And I've always been very interested in aeronautical sciences. And so, after the PhD, then I worked at NASA Ames Research Center in Moffett Field as a postdoctoral fellow. And then I got a job here in St. Louis at McDonnell Douglas, which is now called Boeing. And so I had the privilege actually of working on a variety of products that McDonnell Douglas made. And at that time, McDonnell Douglas was one of the largest companies in aerospace business around the world. And so they had an outfit called the research lab. And so I was hired in the research lab, and quickly I rose in the ranks. And in a few years' time, I became the program director and McDonnell Douglas Fellow. And so then I was able to establish a very highly skilled group of scientists who worked in computational fluid dynamics or aerodynamics, and also in other aspects of computational engineering sciences, which were relevant to the products that McDonnell Douglas made. One advantage to be in that lab is that we could work on any product that McDonnell Douglas made. So I was able to get the business from these divisional companies and then try to address the research needs that they had. And we had at a peak time over about 25 to 30 scientists, and we also used to have a lot of visitors or visiting professors. So we had a world-class group which was very well known in the industry and as well as in the university circles, and we were doing the leading edge research. So I was there for 16 years, and then there was a downturn because of a variety of reasons. And so as a result of that, that group started shrinking, and also the the support that we have had from the corporation was getting more and more limited. And so I thought of actually moving to some other place. And of course, one of the things that I always wanted to do, having a research background, to move to academia. Then I had the opportunity to first move to as a head of the institute called the National Institute of Aviation Research in Wichita, Kansas.
Mhm.
So later on, I joined Washington University because I wanted to come back to St. Louis, where I had spent most of my life. And so at Washington University, I came in 2001, and I have been here now for 25 years. So when I came here, of course, I started working in some aerospace work. So I started working with the Boeing, and even today I have projects and the students part time who work from Boeing with me. So after several years, one thing I had in mind that there is a big problem in terms of the emissions from the combustion of the jet fuel, which is being used in all aircraft, whether there's a fighter or the commercial aircraft.
Mhm.
And so I thought that, there is a need to move to some other kind of fuel that is almost emission free or does not emit the CO2 into the atmosphere. So I started looking into what in those days were very, very early stages. And now it is called the green aviation, sustainable aviation, or environmentally responsible aviation. So there are a variety of names people say, and this has become a very, very important area of research and also in terms of the future aircraft designs and propulsion systems. So the Europeans are looking at it, the European consortiums are looking at it very seriously, and we in the United States are also looking at it. So I became one of the first people actually in the country in around 2008 to give the William Littlewood lecture on the subject of sustainable aviation. And it was not that popular at the time. So that is how I started in the area of the sources of fuel, which can lead to the reduction in the emissions and control the issues related to the global warming and climate change. And so then later on, I also thought that there should be some other sources of energy in general. And in university, one freedom that you have that you can look into any problems of interest. When I was working for Boeing Company or McDonnell Douglas, I was focusing primarily on all problems related to aerospace products. But now I started looking at wind energy, solar energy, energy from the biomass. And over the years, I'm still doing that work. And so I started teaching a course which is called the thermofluid modeling of renewable energy system. So the focus was on the renewable energies. And so I started working on with the students on this subject and also in the area of the sustainable aviation, particularly addressing the propulsion, the alternate fuels. And if you use that, then your design changes. Now, in propulsion system, if you use hydrogen, so you can have a hydrogen fuel cell for short range aircraft, and then you can have a hydrogen engine, which is long range aircraft. One of the difficulty in this acceptance of this technology has been that you will have to create a new engine for propulsion. And so the creation of a new engine means that you will have to invest a tremendous amount of money to start a ground up development of an engine like a hydrogen engine. And also, there are issues involved even with the fuel cell. The technology is not that at a level. And furthermore, the biggest issue also is the infrastructure, that how do you generate the hydrogen? How do you store the hydrogen? For example, it is not easy to store the hydrogen
Yeah.
inside the wing because hydrogen requires 4 times the volume that jet fuel, although its density is much, much better. So, for example, if you have a car and you want to use that car to go to, let's say, 100 miles, then you have a fuel tank. which is run by gasoline. But to go the same distance, you will need 4 times the size of the fuel tank. So that means that you will have to completely change not only the internal combustion engine, but you will have to completely change the manufacture and the design of the car. And same issues are there in aeroplane business. So if we have a new propulsion system, we have to do a lot of research and manufacturing of that, and then see, whether you are able to get that in a certain time, and there has to be a takers of that. There are issues of certification, there is issues of infrastructure, and the whole aircraft design becomes different, because it turns out that if you are going a cross Atlantic flight, you need a fuel tanks that have to be stored inside the aircraft, because otherwise there is not enough place to store that kind of a fuel. The other thing is that hydrogen fuel is stored in the form of a liquid hydrogen. So the liquid hydrogen is at a high pressure in a tanks with a very very low temperature, going back to about minus 200 degrees Fahrenheit. So in that case, of course, that is a new technology that you have to develop with right kind of insulation and so on and so forth. So anyway, this is the background that got me started in the issue of the control of the global warming and the issue of addressing technologies that can address in other areas other than aerospace. So then
Interesting.
we had a in 2008, Washington University started the consortium for clean coal utilization. And so in that consortium, the goal was what they call is to use the coal, but by using the coal, somehow capture the CO2 instead of CO2 going into the atmosphere, then can we sequester it? So that is where the issue of carbon capture and sequestration technology came in. And then also the other idea was that can we generate or have the power plants which do not use a boiler. The standard power plant, the which generate electricity, we basically use primarily the boilers, and then they burn the fuel, that is a coal or maybe coal with some other kind of biomass or something, and then they release what is called a flue gas. So flue gas is a mixture of carbon dioxide, some sulfur dioxide gases, and a lot of other contaminants and some particles that come out, including some water vapor. So that flue gas is just emitted to the atmosphere, and that is the reason that we have a concentration of carbon dioxide increasing continuously. And so the electric power generation has two issues that has to be addressed. And that is, one is that can we have an alternate kind of a power plant in which it is we can capture the CO2 in a much more purer form. And it turns out that there is a technology called chemical looping combustion. So I started working in chemical looping combustion with some students, and I have written a large number of papers in that. And actually, I have written a book also in that particular area. And also, I started looking at that once you are able to have a fixed power plant, and from there, we can capture the CO2 in as pure a form as possible, and then we can take it through the pipelines, and then we can sequester it under the ground and or some other reservoirs where it is possible. So I wrote a book on that also, which came out by Elsevier last year. So I've written book on these subjects because I really got into it. So that is how I got it started into this particular technology area. And I am really still I'm working on it, and I'm very excited about it. So I
Yeah.
think I gave you a very long background. Now, one thing I do
Okay.
want to mention very briefly, that the electric power generation, the source of CO2 is fixed at a location. But in the transportation sector, the CO2 that is emitted from the vehicles, whether it is aviation or it is the trucks or the cars or whatever it is, that is a moving CO2. So a mobile CO2, you cannot control that easily. So it is a much more tougher problem in terms of sequestration than a fixed CO2 that is coming out of power plant.
Yeah.
No, that's good. No, I appreciate the background. I think, yeah, definitely. In the future, we'll have to hear more about your hydrogen work because I think that's a fascinating topic as well. But I think for the conversation today, we do want to focus a little bit on the carbon capture topic. And you talked a little bit about it, but for some of our listeners that maybe want a little bit more, can you talk about just kind of how it works? Like, how do you capture the carbon? Where do you inject it? What do you inject it into? Some of those types of basics for folks to better understand.
Yeah.
So the fixed carbon that is emitted from the electric power plant, so that comes out of the chimney, as we know, and is called a flue gas. And it is a result of the burning of coal or maybe some other material, like you can have a natural gas, and these are all fossil fuels. Now, it turns out that coal is really the one which produces a lot more carbon dioxide compared to, say, natural gas. And then you have other industrial plants. This is in a very impure form in the sense that it cannot be used for creating other chemicals and all that. So it needs to be purified. And so it is purified by using either liquid sorbent, which are called amines, or the solid sorbents. And that is what, and then there are processes called scrubbing and all that. And so they made it possible to make it pure, much more pure. So
Mhm.
you can isolate all the hydrogen sulfide or other kind of parts. You can also remove other contaminants, other particles, because in the flue gas, you have these little particles, which are the coal particles, which have not been totally burnt. So not the entire coal particles get burnt into the combustion process. Maybe 98% can be burned and so on. So this is normally in most of the power plant. The amount of CO2 is there is 90%. Now, in some cases, you can have like maybe 94 or 95%. Now, these power plants, what do you call a post combustion CO2 capture. So there are other alternatives which other mentioned to you, like chemical looping combustion, which can generate very pure CO2, or there is a what is called oxy-fuel combustion that can also generate very pure CO2. But most of the power plants around the world, they have these chimneys from which the carbon dioxide comes in, which has about 90% is a carbon dioxide using coal. And so you can retrofit them to clean it up as much as you can. And so I would say that unless until you have a special technology like oxyfuel or you have a CLC, which are still in the stage of research, there are
Mhm.
not many plants around the world that are using that technology because they are still all coal-fired old technology plant. So let us say that you have captured the CO2, which is quite pure. Let's say 90% or more pure CO2 has been captured. So that CO2 then has to be transported where you can, of course, you can have various purposes for it. You can create chemicals from it. One of the things that you want to do is that you want to sequester it. So for sequestration, you need to have a reservoir. So there are all kind of reservoirs. They are very traditional reservoirs that people have been working for a long time, but they are now empty. For example, in Texas, in the Permian Basin, that is a very well-known set of reservoirs for oil. So the oil is being recovered from that. So the oil first, initially, the oil can be easily recovered, which is called the primary oil recovery. And then it is a little more difficult to recover what is called a secondary oil. And then the little residual that is left after recovering that is called a tertiary oil. And so it is very difficult to recover that, but it is possible. So what you can do is you can take this CO2 and inject into those reservoirs. So they will restore your CO2 and also maybe help a little bit in getting the tertiary oil recovery.
Mhm.
So the oil industry is very interested. And similar is the case what we call EGR or enhanced gas recovery. So the previous oil recovery is called EOR in the literature. So enhanced oil recovery. So in the enhanced gas recovery, you're basically talking about natural gas or methane. And the principle is the same. You inject the gas, inject the carbon dioxide, and then you recover the methane gas. Okay.
Mhm.
And the secondary stage or tertiary stage, but you can recover the methane gas. And similarly, that is called what is called the shale gas recovery. So there are a lot of shale reservoir around the world, including the United States, that you can use the same principle and you can inject the gas. And one of the areas which is in plenty, there's a lot of places around the world, and that is called the saline aquifer. So, saline aquifer, you have to go at a very large depth. And so, the depth of, say, 500 to 1,000 meters or longer. And at that, you have what is called a brine, or that is a which is not a kind of a water that you can drink. It is not drinkable water, but it contains a lot of salt. And also contains other minerals. So if you can inject the supercritical CO2 all the way by some kind of a drilling. And there are companies in the United States like Schlumberger, for example. They are very good at it. They are expert in it, and so they can drill this. And once this CO2 goes there, then it will go through 3 or 4 phases, and there are 3 or 4 mechanisms by which it can get be trapped. Okay, so without going to that details, eventually it gets mineralized by interaction with the brine. And so there is a last phase of, the in which the CO2 can get stored. And once it is mineralized, then it can be stored for a very, very long time, for maybe thousands of years or beyond. So that is the goal of sequestration. So you use various kind of reservoirs. So there is another one I want to mention, which has become very popular now, and particularly in places like Iceland and some places like India and so on. And that is called the basalt-based reservoirs. So these basalt-based reservoirs are the ones in which there are other mechanisms, and these reservoirs are very good in terms of taking the CO2 and storing them. So there are advantages and disadvantages. One of the important thing that you want to choose a reservoir is that the source which is generating the CO2, that is the power plant. From that source, you have to use the pipelines to take it where you can sequester it. So whether it's a saline aquifer, or this is a oil reservoir, or a gas reservoir, or a shale gas reservoir, or is a basalt reservoir, you don't want to carry the CO2 too far away. So suppose you are generating a power plant which is generating CO2 in St. Louis, and you don't want to sequester it maybe 1,000 miles away, because it's very, very expensive to have such a big pipeline and take it all the way. So the transportation of CO2 is a very, very major consideration. So that is why you have to have a right location for the generation of CO2 and right location for the reservoir where you can store it.
So in your recent article, I mean, getting to the location choices and things like that for carbon sequestration, in your recent article, you discussed Google's plan to build a new data center. They're utilizing natural gas with carbon capture. So we talked about a little bit what carbon capture storage is, but how does that work, for these data centers and what Google's doing? I mean, I guess, do you want to dive into what Google's doing a little bit in simple terms?
Okay, I will try to be brief. Actually, every time a question is asked, I go into great detail.
That's great. It's awesome.
So the data center can require as much as 100 megawatt of power. And the 100 megawatt of power is not only used for running the GPUs. A large amount of energy is used for cooling these chips. Actually, 40% is required in running the GPUs, and more than 40% is required in terms of cooling these chips. So depending on the size of the data center and the applications they are interested in, it may be of the order of 100 megawatts. This is a huge amount of energy. It can give you an idea that about the biggest coal power plant that the United States has is of the order 1000 megawatts. So you can see that such a big fossil fuel plant will be needed to run 10 data centers. So the people who, like Microsoft, Amazon, Meta, and Google, they are very interested in developing data centers, not only in United States, but all around the world. For example, Google is setting up two very huge data centers in India. And similarly, they are going all over the world, other companies as well. So it turns out they want to have the energy that is required of the order of, say, 100 megawatts or less, around that ballpark, is emission free, which means that the energy should not use, let us say, fossil fuel, but that means that it can come from a renewable energy. Now, the renewable energy plants are not available that can generate 100 megawatt because all the wind power plant and the solar power plant cannot provide 100 megawatt kind of energy for one particular task. So there is in Illinois a town called Decatur. Actually, I have been there myself. And so they had a plant called ADM, Archer Daniel Midland. And so what they were doing actually, that there is a lot of food crops that come in. So they were using those food crops to generate the biofuel. So of course they were generating a lot of CO2. So they became a part of, maybe I don't remember, but maybe 10, 15 years ago, part of the Midwest sequestration symposium or sequestration kind of outfit, which was based at the University of Illinois. So I came to know about it and I was very interested in this technology. So I went over and checked the whole thing, what is going on there. So that power plant is generating some CO2 and of course it is purified. And after that, they have a pipeline and then they have this Mount Simon formation. And Mount Simon formation is not too far. It's only, which is like a saline aquifer. And so that is available only that within about, I don't remember exact number, maybe within say 10 to 20 miles.
Yeah.
So this was the ideal situation that you have a CO2 generated by a power plant, and then you can take that as much purified as possible as CO2 through the pipeline, and not too far away, you have this availability of a saline aquifer in the Mount Simon Formation. That is ideal for testing out that how will this technology work. So this was used as a test case, and so they tried to sequester this by drilling inside the aquifer, the saline aquifer, which was of course 500 to 1,000 miles underneath the Mount Simon, not miles, sorry, meters underneath to the formation. So they were successful in sequestering the carbon. And all that data is available, that how much they were able to do and what was the size of the injection well and what was the size of the monitoring well. And of course, you have to be concerned about the side effects. And one of them is, of course, you don't want to have all this going on, which is an earthquake prone area, because these kind of sequestration efforts and drilling can sometimes give rise to minor earthquakes. And the other thing that is important also is that the pipeline, etc., that you are installing, everything should be done so there is no leakage. No leakage in the transportation of the gas, and also when you have gone to the injection site, the injection well, etc., there is no leakage around this. And there are cases where the leakage has occurred because of variety of reasons, and they have been identified. For example, there are several sources that the leakage can occur. And one of them is, of course, the pressure inside the pipeline can be very, very high if it is not monitored. and that can give rise to what you call a zipper effect, and that can blow up the pipeline. The other one is the corrosion, because these are not pure CO2. So there is always a corrosion, there is always a little bit of water, and that can corrode the pipeline, that can become weaker, because you expect these pipelines to be used not for a day or a few years, but for a very, very long time. And the second thing is that some parts of these pipes will be buried very close to the ground. And so that is where there could be landslides, or there could be some stresses due to the surrounding kind of earth, or surrounding, mud or whatever it is there. And so there are all kind of that geotechnical regions can be there. And so anyway, the thing is that Google knew that this is the situation. So the Google then signed a contract, which is a long-term contract with this company, and they said that you use natural gas. So natural gas has one advantage, that in contrast to the coal, as I mentioned before, the CO2 is relatively more purer and better. And so they said that if you take the natural gas and generate 100 megawatts or whatever you can generate for us, and then you can sequester all the CO2, then it is emission free. So we can get 100 megawatt of energy for our data center emission free. So the technology was there. It is a tested technology. All the plant was there. ADM plant is there. And then you have a sequestration site, which was already mapped, already studied, and we had a lot of data on it. So this was the ideal situation actually for the Google to sign up this contract. And so that is what Google has done here. Now, when it will become operational, I do not remember very well, but maybe in not too long a time, or very soon. Soon. This is not the only contract that Google has signed. In Fargo, Utah, there is there is a geothermal energy which is being offered by Fargo, and that is the largest geothermal energy operator in the country. And so they have signed a contract with them also to provide a geothermal energy, which is going to be of the order of maybe 100 megawatt or more. Their plan is actually, the Fargo has a plan to generate as much as 500 megawatt of energy by 2026 and 2030, that time frame in 4 years. And so Google has signed a contract with them also to provide that energy. So they may have a data center in Utah, they may have a data center in Illinois, etc. So I think that that is the goal, to have a emission-free energy of very large magnitude, and to be able to have these data center.
Interesting.
That's all great. And we definitely appreciate your time. We've been chatting a lot here. And so I got one more question I want to just run by you. So we talked a lot about the technology, but thinking about the business side of what Google is doing. So there's I guess, an agreement they can enter into, a power purchase agreement, kind of talk a little bit about that and how that's possible because they're using carbon capture.
And so what Google has gone into, and that is called a power purchase agreement. And so the advantage of that is that in this agreement, the buyer agrees to purchase electricity from the seller. And often it is a renewable energy, or it is carbon free. So in this case, you can say it is carbon free because of the sequestration technology, and at a fixed or predetermined rate. So they come into a contract that how much they will charge, and for a certain amount of time. So it could be 10 years, 20 years. And so the buyer is going to pay to the seller, under these conditions in this purchase agreement. So this has several features, that for the buyer, there is no upfront cost. He gets the electricity at a fixed and predictable price. It is a renewable energy or carbon free energy, and all the operation of supplying the energy are handled by the operator or the seller. So it is a very good deal actually for Google. The only crux is that they have to come to agreement that how over a period of time and how much money will be paid.
So just cleaning up some quick math while you're talking about the economics, because that, you know, sequestering the CO2 costs and things like that. But I think you mentioned 90% to 95% of the CO2 emissions are captured. What happens with the remaining 5 to 10%?
Yeah, so that is a really good question. So that is why the desire is in general to have a power plant in which you can capture 99.9% pure CO2. But the reality is that you can capture only 90%. And so this actually the CO2 that is emitted as a flue gas is 100% mixed with other stuff. Like, as I said, there is a sulfuric acid and
Mm.
there are, little particulates and water vapor and all that. So scrubbing and also the sorbents are used to clean it up. Okay, so whatever that rest of is left has to be disposed of. So there is a way to dispose it off. But the thing is that that disposal of the CO2, and again, it turns out that the disposal mechanism that is there for that 10%, which is not non CO2,
Mm.
is such that all these amines and sorbents that have been used, you can retrieve them back and reuse them. So it becomes a economical process. And whatever residual is left after taking out all the amines and sorbents, etc., and reusing them, whatever is left, you have to dispose it off. And that disposal is not a big deal because the idea here is that we don't want CO2 to be emitted to the atmosphere. So that goal is accomplished. So whatever that percent is left and whatever sorbents etc. are left etc., they will be again. There are processes to retrieve as much you can for reuse, and rest of it you have to figure out a way to dispose it off, and that's not a big deal. That is done all the time.
So the U.S. Energy Information Administration reported that despite all of these efforts, right, that Google's doing and all the data centers and things like that, America's carbon emissions rose in 2025. And I think a little bit of that is coal to electricity and other items. But we talk about everything that Google's going through, right? Three dimensions of energy, reliability. I know data centers have a 99.999 uptime guarantee. They need to keep it affordable to make it economical. And then sustainable, which is the CO2 part. And every source needs to be considered. But do you think carbon capture and storage, it sounds like it's necessary, but do you think that'll help continue to meet emissions targets? And then how do you see that fitting into kind of the energy growth or the kind of all energy policy that seems to be the case today?
Yeah, so the carbon capture is one of the technologies. You have to have a suite of technologies and methods. So you cannot give up on the renewables. Renewables are going to should be there. So I think more and more wind turbines and solar panels, because the applications are different. Like solar energy has become very popular in Africa, Asia, other places, particularly for heating and cooling of the homes, because you can easily put them and they have become cheaper. The cost has gone down, they have become economical. So similarly, the wind power is becoming very economical. You can get for 5 cents per kilowatt hour or even cheaper. And the technology has moved a lot. So I think we have to consider all suites of technologies: wind power, solar power, biomass for generating biofuels that can be used in the cars and trucks as well as in the aeroplanes. And carbon capture and sequestration is one of the other ones. Now there is other technology which is also getting a lot of traction, is called direct capture. And in addition to that, some people are also working what is called the solar geoengineering by injecting aerosols in the stratosphere. So I think that right now, given the current scenario, the carbon capture and sequestration has been developed to the degree, and there are players there that it can be deployed and benefits can be done. Now, of course, the energy consumption is going to continue to increase, and particularly as the new technologies for data centers, etc., which are the requirements are humongous. Even though other people in their households and in their businesses, etc., they try to cut down on it, but I think the overall scenario is that it will increase. So it will require all players. It will require the politicians. It will require the manufacturers of or suppliers of these energy sources who are willing to basically develop this and meet the demands. But one thing that the entire population, including the common man, should be focused on, that the climate, situation and the global warming has to be addressed somehow. And so, in some sense or the other, everybody can be a contributor to that. I mean, if I consume less energy in my house instead of wasting it, and there are ways that I can have energy efficient building, my own house or bigger buildings, and it's possible because there are a lot of aspects in a building. And so, if I suppose save 10% of the energy, which means I'm contributing 10% less towards the emissions, because ultimately I am using primarily electricity. So what I'm saying is that the general public and of course, starting from the politicians and the manufacturers, the businessmen, all of them have to become cognizant of it, and we have become very aware of it. I mean, if I go back 20 years, as I said, when I started in this business, people were surprised, what is this going on, how much impact is going to have. And as a matter of fact, I am just like, I have written a very, exhaustive book on the carbon sequestration. So people are not going to willing to pay, if suddenly you increase the price, even if it is a good thing, people want to have a competitive pricing, which means the technology has to come and improve to a level that it is possible for the general public to afford.
Dr. Agarwal, thank you so much. And everybody, thanks for listening. We will catch you on the next episode. Have a good day.
Thank you. Same to you. Bye.